So today we're going to be going through the column with numbers 52 through 62. So let's go ahead and get started with number 52. We want to identify and graph each curve formed by the following. Okay, so if we're doing graphs, let's go ahead and start out with number 52. We have r equals 1 minus the cosine of theta. Okay. Okay. So we know that when we have a plus or minus, this is going to be some sort of polar limesone. So first off, I know that it is a limesone. The first thing with limesones is I need to identify my A and my B. In this case, my A is 1 and my B is also 1. I'm dealing with a minus sign, so I know with the cosine, the graph is going to be centered on either cosine or sine. My graph is going to be centered on the left axis. I'm going to take A divided by B, which is going to be 1 divided by 1, and I get a value of 1. When I get a value of exactly 1, I know this is going to be a cardioid. So I'm going to identify this is a cardioid limesone. We remember that cardioids are going to have an inner loop that is equal to 0. So in essence, we say that it does not have an inner loop. And then the few points that we need to graph on this cardioid, let's go ahead and do that right here. Okay, so I know that this graph, like we said, is going to be centered over here on the left. We have a couple points that we're going to be plugging into this graph. The first point is I know I go up and down a total distance of A. So if I have an up distance of A, I have 1, a down distance of negative A, which is negative 1. So I have these 2 points on my graph, and I'm actually going to do these in red. Not that you can tell on these 2 points, but oh well. I also know I go out a total distance of A plus B. So I'm going to go out A plus B, which is going to be A plus B is a distance of right here, which is negative 2. Awesome. And so when I graph this, I'm going to connect smoothly all of my points, loop through that smoothly. And then right here is where the loop, I actually loop right here, but the loop is so tight because A and B are equal that it's non-existent before it continues the loop, continues the loop, continues the loop. Boom. And there we go, we have our cardioid. Okay. That was question 52. Let's try question 53. Okay. So question 53 is r equals 3 plus 2 sine of theta. Okay, so we know because we have a plus or minus right here, this again is a limesone. So I have a limesone. I need to first identify my A and my B. So my A is 3 and my B is 2. Because this is a sine and it's positive, let's see, on the axis, I have positive cosines and positive sines. I know the positive sign is going to be centered on this upper axis. The next thing I'm going to do is I'm going to take A divided by B, which is 3 divided by 2. That's 1.5. This is greater than 1, but less than 2, so I know this is going to be a dimpled limesone. Meaning our cardioid right here actually touches and has something of a loop. Dimpled limesone is going to be out here, and it's just going to bounce somewhere out and about. So let's go ahead and set up our first graph. Okay, so I need a couple things. Again, it's centered on the upward axis. So I have a distance from the upward axis. I'm going to go to the left A and to the right A. So if I go to the left, let's say negative A, and to the right positive A, that's going to be a distance of 1, 2, 3. Right here of negative 3, and a distance of 1, 2, 3. of positive 3. Next, I know that my distance out is going to be a plus b. So my distance out is a plus b because it's centered upward, which is 1, 2, 3, 4, 5. Oh, should have made my graph a little bit taller. It's going all the way up. And because this is a dimpled, I know a minus b would leave me right here, but that would imply an inner loop. So the dimple is going to be on the other side. So I have a negative a minus b. Awesome. And so I know I always start out on the positive, and as I go through this, I'm going to curve gently. And then continue on. And so we see that dimple is a general curve. It's going to eventually hit a sharp point right here before that point begins to loop. So right here, there is no point. It's just a gentle curve. It goes slightly beyond that value and up. And this is what we see as a dimpled limacone. Okay, that was number 53. Let's take a look at 54. Okay, so I have 54 is r squared equals 9 sine of 2 theta. Now this one's going to be a little trickier one because we do have to do a test graph before we do the full graph. Okay, so with an r squared, my first step is to break that down into a regular equation, which means I square root both sides. So r is, the square root of 9 is 3, and the square root of that is just root sine of 2 theta. And because I artificially introduced the square root, I have to take both the positive and negative values of this. The next thing, there is no plus or minus, so this is not a limacone. This is going to be a rose petal graph. So first off, I know this is a rose petal. But because I'm dealing with the square root sign, it's not just any old rose petal graph, it's a lemniscate, which is going to be So that's the type of graph that we're dealing with. And now this, for the most part, follows the same rules as rose petals. I know that my petal length, and let's do this in green, my petal length is going to be 3. I know that I'm going to have, because this is even, that's 2n, or 2 by 2, which is going to be 4 petals. We will see that that will be abbreviated here in just a few minutes because of this square root sign. But in essence, I'm going to graph a test graph of this. So let's see what the basic graph would be. Okay. So what I've got right here is I know I'm dealing with a sine graph. I have both a positive and negative sign. So in essence, I'm just going to graph it. I know the sine is positive up here, and the cosine's over there. So I'm going to balance it both above and below. Because it's even, it doesn't really matter. I know I have a distance of 3 on my rose petals. Because there are 4 of them, it's going to be 1 per quadrant. So let me break out the compass and set a radius of 3. And because they're evenly balanced, I know it's going to be directly in that diagonal. So 3. 3. 3. Make sure I'm still at 3 yet. Still at 3. And 3. Okay. So that's my first sketch. Now, I'm going to go ahead and I'm going to say, hey, let's connect all these. And because I have to start out on the 0-degree angle, I'm going to say, hey, actually, before we even begin that, I know where my 4 petals are. Let's take a look at the actual sine graph and see what we're about to do. Now, the sine graph, if this was just a regular sine graph, let's say this is y equals 3 sine of 2 theta. First off, This graph we know would have an amplitude of 3, which means it goes up and down. It goes up to 3, down to 3, up to 3, down to 3. Let's set that up. Okay. So that has a distance of 3 and -3, which is going to be the radius of this graph. It's going to be going positive, negative, positive, positive, and for the second loop, it's going to be negative. For the third loop, it's going to be positive, and for the fourth loop, it's going to be negative. We also know that the period is going to be 2 pi divided by b, which is 2 pi divided by 2, which is just pi. So I know the period right here is going to be by pi, so over here is going to be by 2 pi. So right here are all the values that we're going to see in this entire graph, because remember we go to pi and then back to 2 pi. The problem that we're going to run into is whenever this graph is going into the negative area, I can't take a negative square root. The graph is going to disappear. So for all of this part of the graph, I'm not going to include it. For all of this part of the graph, I'm not going to include it. So I'm only going to have a graph from this point until half of that, so to pi over 2, and then from this point to 3 pi over 2. I only have the positive aspects of the graph, which again, let's take a look. So from 0 to pi over 2, or from 0 to 90, I have a value going out to 3. So my graph is going to go out to 3 and back. When I move into the second quadrant, my graph dips negative. So albeit I would like to draw a rose petal out here, it's a negative rose petal, so it's in here. This part of the graph is not included. Not part of the graph because it's negative, and I can't take the square root of a negative part of my graph. But when I go into the third quadrant, right here, I'm good. So it comes and it says, hey, there we go. And for the fourth quadrant, which should be over here, it's negative, so my radius is going to end up pushing me into this area, which I know is, again, I cannot take the square root, so I'm not using either of those. So my graph is only going to include my first quadrant and my third quadrant values. It's not actually going to include the graphs in red. So this is going to be r equals plus or minus 3 root sine of 2 theta. And there we go. It's this. Now, it's actually doubled up. If you want to say, well, why not the plus or minus? Well, remember, it's not plus or minus. I can't take the square root of a negative. But this graph is the positive if I take the positive 3. And if I take the negative 3, I'd include this over here. Can't include that. Once I get into the third quadrant, I would have the positive distance to 3 and the negative distance to 3, which is, again, that exact same petal. So both these petals are included both in the positive and in the negative. Okay, and so that's 54, which brings us to question 55. So we're converting these polar equations to rectangular form. Let's go ahead and start on a new sheet of paper. I have this equation of r equals -3 cosine of theta. So let's take a look at this. So we remember the fact that converting a polar equation which deals with distance and theta into a rectangular equation deals mostly with the r has to be converted into, we know that any set of coordinates was some sort of x value and y value, which gave us a radial distance. And we can convert any of these as r squared is x squared plus y squared due to the Pythagorean theorem. Second, we remember that sines, cosines, and tangents deal with the unit circle. So sine is y divided by r, cosine is x divided by r, and tangent is y divided by x. So I can convert cosine into x's and r's, I can convert r's into x's and y's, and that's it. So we're going to go through these two maneuvers to change this back into x's and y's. So my first step is to convert the trig functions into their respective values. I know cosine is x over r, so I have r equals negative 3, x divided by r. I notice that r is on the bottom and on the top here, so I can remove it from the right-hand side by multiplying both sides by r, which would give me an r squared equals negative 3, x. So the cosine is gone, and I'm left with only r's. Conveniently, r squared can be replaced with this. So I'll get x squared plus y squared equals negative 3x, and that is my rectangular form equation of that polar equation. Okay, that was number 55. We're going to take a look at 56. Okay, so number 56, we have r equals 2 divided by negative 4 sine of theta plus 5 cosine of theta. Okay, so again, we're going to use the same two sets of tools that we have. We know that on any equation we have an x value, a y value, which gives us a distance using the Pythagorean theorem. X squared plus y squared is r squared. But before we get to that, we deal with the unit circle. So sine is y divided by r, cosine is x over r, and tangent is y over x. Okay, so the first thing I'm going to do is get rid of sine and cosine using these two values. So let's make sure, I'm going to do these in red and green this time so they stick out a little bit more. Okay, so my r is equal to 2 divided by negative 4. Sine we said is y divided by r plus 5. Cosine we said is x divided by r. Okay. Now the first thing, before we even attack this side of the equation, let's simplify this fraction. So I've got a couple steps to do here. 2 divided by, both of these equations are divided by r, or both of these terms are divided by r, so I'm going to combine them. I have a negative 4y plus 5x, both divided by r. So complex fraction, I'm going to keep, change, flip, which means I have r equals 2 over 1 times r over negative 4y plus 5x. Okay. My next step is to move these two together, but I notice that the r is in the top of both equations. So if I multiply both sides, let's do this in purple, times 1 over r, my r's cancel out. I do not have r anymore. And I'll have 1 equals 2 divided by negative 4y plus 5x, because that is multiplied by the 1, so it doesn't change. Now, technically speaking, I could stop right here, but we want to leave these in positive exponents if we can. So I'm going to do one final step, and I'm going to multiply both sides by that negative 4y plus 5x. So times 1 gives me negative 4y plus 5x equals 2, and we're going to leave that as our final equation. We could stop here, but we're going to take it one step further and stop right there. So that was 56. Let's take a look at 57. So 57 is r equals 4. I don't got a lot to go on here because there's no trig functions, but I do remember the fact that any unit circle has both an x and a y value, which begets me an r. So I can use x squared plus y squared is r squared, and I have an r if only I could square it. So I will. R squared is 16. Now I can replace it, which means x squared plus y squared is 16. And there's a rectangular form. That was number 57. Let's take a look at number 58. Boom. Okay. So I have r equals 6 times the sine of theta. Okay. So again, the tools that I have at my disposal are going to be, if I have some sort of unit circle with an x and a y, it begets me an r. So I can use the Pythagorean theorem, x squared plus y squared is r squared. Second, if I have any trig functions, I know that sine is really just the y divided by r, cosine is x divided by r, and tangent is y divided by x. So let's take a look. I have a sine function, which is going to be y divided by r. So r equals 6 y divided by r. If I want to get that r out of the denominator, what I do is I multiply both sides by r. So I get r squared equals 6y. And lo and behold, I set myself up for the next step. I know how to replace r squared. So I get x squared plus y squared equals 6y. And there we go. So that was number 58. That brings us to question 59. So let's take a look at 59 and see where exactly we're at. Okay. We're going to convert the following rectangular equations to polar form. And so 59 is 5x minus y plus 8 equals 0. Okay. So let's remember, just like converting polar to rectangular, we use the unit circle. We also use the Pythagorean theorem. With this, we don't necessarily have it set up for the Pythagorean theorem, but what we can do is we can set it up for the unit circle. So I'm going to come right, let's do it right over here. So for the unit circle, sine is y over r, cosine is x over r, and tangent is y over x. If I want to convert y's or x's to r's, I'm going to use the two relationships which deal with y's and x's and r's, which are sine and cosine. Tangent won't work because I can convert y's into x's, and we're going to ignore that for right now. But we'll see why here in just a moment. So let's write out this relationship. The sine of theta is equivalent to y divided by r. Now if I want to replace y, let's isolate the y. So r sine of theta is equal to my y. That means r sine theta can replace any y. Likewise, if I look at the cosine relationship, the cosine of theta is x over r. If I want to replace my x, let's isolate x. So r cosine of theta is equal to x. So anytime I see an x in an equation, I can replace it with something that is not an x and not a y, but an r and a theta. If I see a y in an equation, I can replace it with something that's not an x nor a y, but an r and a theta. And lo and behold, I have exactly that going on over here. Let's zoom out just a bit. Okay. So I know that I can replace my y, and I can replace my x, and I will do exactly that. So 5 times blank minus blank plus 8 is 0. My x is replaced with r cosine of theta. My y is replaced with r sine of theta. Perfect. So let's go ahead and solve this. Now, typically a polar equation, I could stop right here and say, well, this is polar. Standard polar form denotates that I isolate the r. So let's go ahead and work this. So if I have 5r cos theta minus r sine theta plus 8 is 0, my first step is I notice that both these terms have an r. So let me factor it out. 5 cos theta minus sine of theta plus 8 equals 0. So now I notice I can isolate this r by removing the 8 and by dividing this. So 2 steps and we're done. So let's get rid of the 8. 5 cosine of theta minus sine of theta is equal to negative 8. And then we divide out the remainder. So r is negative 8 divided by 5 cosine of theta minus sine of theta. And that is a standard polar form. The r is isolated. I don't have a single x nor y because I replaced all of them. Awesome. So that's number 59. Let's take a look at number 60. 60, x squared plus y plus 3 squared equals 9. So now this is really close to what we wanted to do. In fact, we have a couple different sources to solve this right here. So the first source means that we need to come over here and redenotate this. Using the unit circle, Sine is y over r, cosine is x over r, and tangent is y over x. If I want to change y's into r's and x's into r's, I'm not going to use tangent. I know that the sine of theta is equal to y over r, which means y has a good replacement of r sine theta. I can replace y with non-xy counterparts. For cosine of theta, that is x over r, which means x can be replaced with r cosine of theta. Good replacements. So I could just jump straight in there and solve that. But I have a third option. I could get my x squared and y squared, which would be my r squared. That might actually be a slightly faster method, but let's assume that we don't spot that I could do that rather quickly. And let's take the long method, and we'll come back and cover that short method here in just a moment. I know that x and y can be replaced, so I'm going to leave blank squared plus blank plus 3 squared equals 9. X is going to be r cosine of theta. Y is going to be r sine of theta. Okay. So now with this method, the first few steps that I have to do is I'm going to square these. So I have r squared cosine squared theta plus, in this case, I'm going to have to FOIL this because I have a binomial. So r squared sine squared of theta, double the product, plus 6 r sine theta, and square that, plus 9 equals 9. The first thing I notice is that those 9s are eventually going to cancel out, so I'm going to subtract them in one step here. But before we get there, I have r squareds that I'm going to factor out. Cosine squared of theta plus sine squared of theta plus 6r sine of theta. And I'm going to go ahead and subtract both these 9s right off the bat and say equals 0. Okay, so I have an r squared, an r, and a 0. Because both these terms have an r, I can divide all 3 terms with an r, and 0 divided by r is going to be 0. So in fact, it reduces this to r cosine squared of theta plus sine squared of theta plus 6 sine of theta is equal to 0. All terms have been divided by r. The second thing I notice is I have a Pythagorean identity sitting right here. Cosine squared plus sine squared is 1. So it's really saying r plus 6 sine of theta is equal to 0. Isolate my r by subtracting that. R equals negative 6 sine of theta. Awesome. The alternative method to this is by using the Pythagorean Theorem. Remember that if we have the unit circle and I have any triangle x and y are, x squared plus y squared is r squared. I could use that as well. And before I even work this, I could work this. Let's write this over here. X squared plus y plus 3 squared equals 9. I can do a different method by foiling this first. X squared plus y squared plus 6y plus 9 equals 9. My x squared and y squared is replaced with the r right here. So I have r squared plus 6y, and I'm going to subtract my 9s, equals 0. So I only have one replacement to do. I'm going to replace my y with r sine theta. R squared plus 6 r sine theta equals 0. Because both these terms have an r, I get rid of it. R plus 6 sine theta is 0, and then subtract it. No matter which method you use, you get r equals negative 6 sine theta. This is a little more in-depth. This is a little more abbreviated, but you have to spot that you can see that you'll eventually create that Pythagorean identity right here. You end up getting the same thing over here, but whichever method you prefer. That was number 60. Let's take a look at number 61. Okay. So 61 is x squared plus y squared plus 2x plus 5y equals 0. Okay? Now this is going to involve that shortcut of which we just saw up here. So I have a couple ways that I can attack this. We remember that sine is y divided by r, cosine is x divided by r, and tangent is y divided by x, which is, as of this point, completely useless. Thanks, tangent. To rewrite sine, I know sine of theta is y divided by r, so y can be replaced with r sine of theta. We know that cosine of theta is x divided by r, so x has a good replacement of r cosine of theta. We also know that on the unit circle, any point x, y will produce an r, so using the Pythagorean Theorem, x squared plus y squared will equal r squared. Option 3. So what I notice right here is I have that third option, x squared plus y squared is r squared. So I'm going to replace that. I also notice that I have an x that needs to be replaced and a y that needs to be replaced. So I'm going to do 3 separate replacements all in the first go. So replacement 1 plus 2 replacement 2 plus 5 replacement 3 equals 0. X squared plus y squared we know is r squared. 2x is going to be r cosine of theta. 5y is going to be r sine of theta equals 0. Okay? At this point, all 3 terms all have an r, so I can get rid of it by dividing everything by an r. So I get r plus 2 cosine of theta plus 5 sine of theta is equal to 0. Subtract these 2 terms, and we're done. Boom. And there we go. So that was number 61. Number 62. So we're going to rewrite these in standard form, graph them, and list each characteristic of each conic section. So we're going to figure out what each of these represents for A, B, and C. So let's go ahead and start out with the first one. And because we're going to be graphing them, let's go ahead and do this on graph paper. So 62A. Okay. So 62A is 4x squared plus y squared minus 8x plus 6y plus 9 equals 0. Okay. So we've got to do a lot to this. So the first thing that we need to do is I need to list my x's and my y's together so that I can separate them out and complete each square. So that means I'm going to list this negative 8x right here. So let's see, 4x squared minus 8x plus y squared plus 6y plus 9 equals 0. And now what we've got to do is in front of my squared terms, I have to factor out any coefficients, which means that 4 and nothing to factor out of my y squared. So I'll factor out a 4, and I'm left with an x squared minus 2x, and I'm going to leave a space. I'm going to say y squared plus 6y, and I'm going to leave a space, plus 9 equals 0. We're going to see what goes on in these spaces. So in order to turn this into a conic equation, I need this to be x plus or minus something squared, which means I need to complete the square. So I'm going to take that middle term, the negative 2, and cut it in half. So negative 2 divided by 2 is negative 1, and square it. So I'm going to add a 1. But if I add a 1 to the left part of the equation, I have to also add a 1 over here. But it's not just a 1. That's a 1 times 4. So I have to add a 4 over here. And then I do the same thing right here. I'm going to take that 6 and I'm going to cut it in half. So 6 divided by 2 is 3, and I'm going to square it, which is 9. And I already have a 9, so I could add a 9 here and add a 9 here, but that seems a little redundant, so I'm just going to include that 9 as part of my completed square. Okay? And so the next step, now that I've completed the square, I can immediately factor those into 4, and that what I just did right here is going to be an x minus 1 squared,
because if I factor this, x minus 1 gives me that quadratic. And then over here, I'm going to say plus, that 3 right there is going to be y plus 3 squared, because if I factor this, I'll get that, equals what I've got over here is 4. Okay, so now this is almost ready. I have my squared and my squared, but I can't have coefficients in front of them. So I'm going to divide the entire equation by any coefficients. So I divide the entire equation by that coefficient, which is 4, which gets rid of this over here, and I have my x minus 1 squared. Doesn't right here, so I have y plus 3 squared over 4. And then that divides by 4 into a 1. Now what we see right here is we've created the equation of an ellipse. Okay? And we know the equation of an ellipse is going to be x minus h squared over a squared plus y minus k squared over b squared equals r squared. Actually, it equals 1. And so we know that that a squared, so a, let's actually sketch the ellipse real quick. So if we have some sort of general ellipse, I know the vertex right here is at hk. I know that the distance right here is going to be a. I know the distance right here is going to be b. And I know that the focuses, or the foci, are going to be here in the middle. So let's do them in purple, which is how we would draw the ellipse. And those foci are going to be at h plus this thing that we call c. And the way that we find c is in a regular ellipse, we take a squared minus b squared equals c squared, which will give us what our c is. Okay, so that's all we need to graph. So we've got all the information we need tumbled up right in here. So let's go ahead and get to work. Zoom out so that we can move over to the graphing area. So what I know is that my vertical height is my b squared. So my vertical height is going to be the square root of this, which is 2. The horizontal width is going to be the square root of this, which in this case is just 1. Square root of 1 is 1. So it's actually a taller ellipse than it is wide. I know that the center of my ellipse is at positive 1, negative 3. So let's go ahead and, ooh, it's a horrible axis, but we'll stick with it. Okay, so if I have my x and my y, what I know is that my focus is at, we said the opposite, so 1, negative 3. 1. Okay, we know we have a vertical distance, we said, of square root of this, so 2. So I am going to go up 2 and down 2. And I know I have a horizontal spread of the square root of this, which is 1. So I have this and this. So I'm going to sketch my ellipse right here. If we want to label this, we could say that this is at 1 comma negative 3. I know that I have these points, which if that's a distance of 1, this is going to be 2 comma negative 3 and 0 comma negative 3. I know the top and bottom points are going to be, if that's 1 negative 3, that's going to be 1 negative 1. And this is going to be at 1 negative 5. So I've got my 4 corners right there. And the last thing is I need to label my foci, which I don't exactly know what my foci are right now. Because my foci are going to be up here, I'm still going to take a squared minus b squared. In this case, if I try and do a squared minus b squared, that will give me my foci out to the side. I'm going to flip it because it's a vertical ellipse. I'm going to take b squared minus a squared, which will give me c squared. B squared is 4, a squared is 1, 3. So the root of 3 is c. So my distance up and down is root 3. So I'm going to put my point right here, and right here. I'm going to say that this is -3 minus root 3. Oh, 1 comma. And this is 1 comma, -3. Let's see if that was -3 minus. This is -3 plus root 3. Boom. And there we go. We have all the information we need on that graph. Where the two foci are, where the vertex is, and where all the points around the edges are. Awesome. Okay, so that is number 62A. I'm still going to draw a line right here, just because it seems appropriate. Let's go 62B. Okay. So 62B is 9x squared minus 4y squared minus 18x minus 8y minus 31 equals 0. Okay. Now this is all the information we need to set this up. So we're going to do the same thing that we just did, and I'm going to group my x's and group my y's together so that I can complete both of those squares, which means this is 9x squared minus 18x minus 4y squared minus 8y minus 31 equals 0. Now one of the things I do notice is that y squared has a negative term, which I immediately know that if this works out, this is probably going to be a hyperbola. So I'm going to write that down just because I noticed that that is a negative y squared, probably a hyperbola. But we're going to test it out. So the first thing I'm going to do is I'm going to factor out that 9 and that -4. So I'm going to factor out the 9, x squared minus 2x, and I'm going to leave a space. Y squared, factor out the -4, that becomes plus 2y, leave a space, minus 31 equals 0. So for my x, I'm going to complete the square. Half of -2 is -1. Squared is 1. If I add a 1, I'm eventually going to multiply that times 9, so I'm going to add a 9 over here as well. Do the same thing right here. Half of that 2 is 1. 1 squared is 1. If I'm going to add a 1 over here, it's actually times -4, I'm going to subtract a 4 over here as well. What this allows me to do is this allows me to have a 9, and this is an x minus 1 squared minus 4, and this is a y plus 1 squared. I'm going to go ahead and move that 31 over. So that's actually a positive 31 plus 9, which is 40, minus 4, which is 36. Okay. The next is I can't have any of these coefficients. So I'm going to go ahead and I'm going to divide the entire thing by both a 9 and a 4, which is dividing by 36. So when I divide the 9, those cancel out. I still have to divide by 4, so I get x minus 1 squared divided by 4. The 4's cancel out right here, but the 9 doesn't. So y plus 1 divided by 9. Both the 9 and the 4 cancel out right here, and I'm left with a 1. So this is all the information I need. If you wanted to take it a step further as opposed to what we did with the last one, is we can rewrite it as x minus 1 squared over 2 squared minus y plus 1 squared over 3 squared equals 1. And that will give you your A and your B much more explicitly than what we had right here. But this is the equation in standard form, and just like we thought, this is a hyperbola. It's like an inverted ellipse. So my equation in standard form, listed. What we know about a hyperbola is we still use the same things that we did for A and B. The only thing with a hyperbola is that we're going to take a box with a vertex, and I know that this is going to be my distance A, this is going to be my distance B, and I'm going to use that to sketch an asymptote and an asymptote, which will give me my two vertices. And then my focuses, or my foci, are going to be over here. And my Fochi on hyperbola is going to be found at a squared plus b squared equals c squared. And that's going to give me my distance right here of c. Or actually, from the vertex, we have this is going to be c, not that little distance. And so that's all we're going to be doing. So let's go ahead and set that up over here and take a look at everything that we've got. Okay, so I'm going to be moving this to the right one and down one. Horrible axis yet again, but we're going to go with it. Okay, so my vertex in this case is going to be right one, down one. So there's my vertex. I know my A, which is my left-right span, is going to be the square root of that, which is 2. So I'm going to come out here, 1, 2, and back 1, 2. I know my B, even though it's not on the actual graph, it's going to allow me to sketch my asymptotes. So my B is going to be 3. 1, 2, 3. 1, 2, 3. And in between these 4 points, I'm going to draw myself a nice little square. Okay? And in that square, these 2 corner points, this is what gives us our asymptotes for a hyperbola. Right here, right there. So we're going to do the asymptotes. How about we do them in blue? We have another one right here. So those are our 2 asymptotes, which means our hyperbola touches this point, curves up, curves down towards those asymptotes without touching, it curves up, and curves down without touching, continues on, and then I have 2 focuses which are a little beyond here. So what I know is that these focuses, I want to get these focuses a little more exact than the last ones. So I'm going to say a squared plus b squared. That is going to be 2 plus 3 is c squared. 5, or root 5, is our c. And figure out what root 5 is. Let's go ahead and say root 5 is roughly 2.23. So roughly 2.2. So I know that, okay, a distance of 2.2, my focus is really close. 2.2, my focus is really close. Okay? So we've got our entire graph set up. Now all we need to do is list our points. My vertex, we said, was at 1, -1, 1, -1. My 2, well, that's actually the center. My 2 vertexes are actually over here. So let's say that's at 2, 3, -1. So 3, -1. And this is at -1, -1. My focuses, or my foci, are going to be at, let's see, that is 1 plus root 5. 1 plus root 5, comma -1. And this is going to be 1 minus root 5, comma -1. Okay? Now, sometimes what you'll need to do, depending on the context, is you might need to label your asymptotes. So this looks like a line I intercept at -3. I have a slope of 2. So y cannot equal, no, it's a slope of positive 2, 2x minus 3. There's the equation for my first line. My second line, let's see, I have an intercept at 1, and I have a slope of -2. Y can't equal -2x, and we had an intercept at +1. Cool. So you might need to label your 2 vertices, but that's all the information we need to graph this. Awesome. So that brings us to question 63, or 62C. Okay. And 62c is going to be x equals negative y squared plus 2y minus 6. Now the first thing I'm going to notice is that the x is not squared. So this means it is not either a hyperbola or an ellipse, but instead a parabola. I also noticed that it's not x squared x in that, which means it's not going to be a up and down vertical parabola. It's going to be one of these left and right. Now, if positive x meant up and negative x meant down, positive y is going to mean right, negative y is going to mean left. So we're looking at a parabola that opens up to the left. So that's what we got. The second thing that we need to do is we could do this a couple different ways. We could list where the vertex is using the negative b over 2a technique. But what that's not going to give us is not going to lend us towards where that focus is. And in order to do the focus, we can set it up into the same equation, or the same sort of form as we did previously. So let's go ahead and convert this into that same squared term that we've been doing. So the first two steps is I'm going to move this 6 over and get rid of that negative. So if I move the 6 over, I have x plus 6 equals negative y squared plus 2y. The next thing I'll do is I'll get rid of that negative by dividing this side by a negative. So negative x minus 6 is y squared minus 2y. Okay. Now with the y squared, I'm going to go ahead and I'm going to take that b, negative 2, cut it in half, which is negative 1, and square it. So if I add a 1 over here, I'm also going to add a 1 over here. What that allows me to do is I have a negative x minus 5 is equal to y minus 1 squared. Perfect. So now this expression, once I factor everything out of the x, is ready to go. So I'm going to factor out that coefficient, which is a negative 1, x plus 5 equals y minus 1 squared. This is everything I need to know to graph a quadratic. My first thing I know is that my vertex is again at hk, and I know that this is going to lend me to where my focus is. So let's go ahead and first off graph where my focus, or graph where my vertex is. Whoop, that's a slightly better but equally horrible graph. Let's zoom out just a bit so we can see all that. Okay, so my vertex is at negative 5, positive 1. So I'll come over here and say 1, 2, 3, 4, 5, positive 1. Probably should have moved my graph over a little bit, or move that vertex over, or that axis over, but we're going to keep going. So negative 5, positive 1. What's going to happen next is I'm going to have to figure out where my focus is. And the focus that we get of a quadratic that's in this form is going to be, this is 4p, and my focus is going to be this negative 5 plus or minus the p depending on which direction. Because we know it's opening to the left, it's going to be negative 5 minus p. So let's figure out what p is if 4p is negative 1. So 4p is negative 1, which means p is negative 1/4. So that means that my focus is at negative 5 minus 1/4. Perfect. So negative 5 minus 1/4 is going to be right there. It's not a very big focus, so not a very big gap, but we can make it work. So we're going to label all of that. Boom. So we see all points are bent around that point right there. We'll label everything we know. This is negative 5, 1. This point in here is negative 5, well, minus 1/4. We can do that. That's actually negative 21/4, 1. Awesome. And so that's all we really need to do. There we go.